Okay, so vectors are always represented with arrows. Resultants are what connect head of or tail of the first vector to the head of the last vector. Doesn't matter how many component vectors you have. The resultant is still connecting tail of the first. I did that very badly. I apologize. Let's do that there. To head of the last. And it's really easy if you use the line tool on Doceri to get a nice straight line. That's your resultant vector. Doesn't matter how much you wiggle around, doesn't matter how far you go. Now the cool thing about graphical, doing graphical solutions for vectors is that if you are very careful and you are cautious with scale, you can actually solve vector problems without doing any math. Other than the scaling math. So if we're told that someone travels, pardon the messy handwriting, if you travel 12.5 meters east, then turn and travel 5 meters at 30 degrees north of east, what is the resultant displacement? Important to note, resultant displacement must include two things. What are they? The displacement and the direction. Yeah, that displacement has to have a direction. If you just give me, 13.2 meters, that's wrong. That's half off. It's, if it's a 10-point problem, you just lost 5 points. Okay, so to scale these, what we're going to do, okay, so two things. Number one, these are actually easier on paper than on the computer. Though, if you want to try doing them on Doceri, you'll need to get yourself a good image of a ruler marked in centimeters and a good image of a protractor. The challenge is not scaling those objects when you move them. Because doing graphical interpretation of vectors relies on your scale being consistent. Now the bonus that we have, of course, is the little, the graph paper. So we can say that that graph paper is, let's go to the medium graph paper maybe, that might be even easier. We can say that that graph paper is maybe 1 block equals a half a meter. So let's get this scaled up to the point where we're looking at, and I very often do really easy scales like 1 centimeter equals a meter, 2 centimeters equals a meter, and it keeps the math fairly simple, or 10. 1 centimeter equals 10 meters, so if you have a 60-meter vector, that's 6 centimeters. You want to keep the scaling easy for yourself. Okay, so I'm just going to use the graph paper because I think using the ruler is going to be more challenging than it's worth, frankly. So I'm going to kind of set that aside. So I have 12.5 meters of travel. That means that I need a line, if I'm saying that 1 block equals 0.50 meters, then that means that I need a line that is 25 blocks long. So I'm going to start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I've obviously run myself out of scale. That's a problem that we have on paper too. You have to really plan for your scaling. So what I'm going to do is, frankly, I'm going to start over. I'm going to change my scale because I can't fit this drawing on this screen. Sigh. I'll just get rid of that. I'm going to change back to the small blocks. And I'm still going to say that 1 block is equal to a half meter. So now I need 24 spaces. This is so much easier to do on paper. I apologize. This is the one thing that really is hard to do on a screen. So if I'm starting here, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I'm going to do a line from there to there. That's my first vector. And I'm going to label that. And because we're talking about displacement here, I'm actually going to do D1. and that is equal to 12.5 meters east. I want to make sure I have a good arrow on that. Do not leave the arrowheads off of your vectors. If you do, you will cause yourself a world of heartache and grief. It creates lots of opportunities to screw things up. So now comes the more interesting part. I need to turn and go 30 degrees north of east. So this is where in the video I showed the little compass rose trick. You're going to want to put that compass rose right there. And you're going to need a protractor. Whoops, not like that. And you're going to set your protractor with the little 0 dot right on the corner, on the center of your compass rose. And you need to draw a line that goes out through, whoops, from that center dot out through 30 degrees. Okay. Now, here's the tricky part on this, because I can't count squares to get a 5-meter line, geometry being what it is. So I know that that's 30. Let's see, and let me double check something here. Select. Scaling, no, scaling shouldn't change that. Okay. So let's get that out of the way. I'm going to need the ruler, and this is going to be, I tried really hard to get this transparent. I think I can do it this way. So if this is really challenging on the screen. So here's what I'm going to have to do. I'm going to have to go in and highlight one block, and I'm going to make that a 1/2 centimeter and scale my ruler appropriately.
Why can't you just do it and then move the arrow?
What do you mean?
Like copy and paste it.
Ah, clever. Let me try that. But let me also try this approach. Reason being, when you move stuff, it's really easy to change how long it is. So that's kind of why I'm going to all this trouble. We will try that, but I don't think it will work. So let's scale this ruler up a little bit. Okay. So at this point, 1/2 centimeter on my ruler is equal to the distance of a block. So I'm going to try really, really hard not to change. I just changed it, didn't I? Sure did. See, it's nearly impossible. This may not be possible to do on the screens. So I'll tell you what. Let's walk through doing this on the board, sort of the old-fashioned way, because I think the technological difficulties cannot be overcome. So I'm going to pause this. I'll take pictures of what we do on the board, but I don't think this can be done on the screen. This is the first year I've actually tried it on the screen, and I think it just doesn't work. Okay, so we're moving 12.5 meters east. I'm going to go ahead and use 1 centimeter. 1 centimeter equals 1 meter. So I'm going to do 12 and a half centimeters. Boy, this is tiny. Let me change my scale. When you're doing this on paper, you're going to change your scale repeatedly, because I'll give you a problem where I screwed up and you have to turn your paper sideways and do it corner to corner to get the scale to work. It's okay. You'll manage. So let's call 2 centimeters a meter, which would mean 25 centimeters. All right. So 10, 25. Okay, a little bit better. So I'm going to label this as displacement 1, 12.5 meters east. Now I have to turn at 30 degrees north of protractor. Where'd it go? There it is. North of east. So I'm going to take my protractor and I'm going to put the little bubble, the little dot, right on the tip of the first vector. I'm going to make a mark out here at 30. Okay, so I made a mark at 30 degrees towards the north from due east. We'll practice this. Now I'm going 5.0 meters. So that's going to be 10 centimeters on my scale. Okay. So there are my two vectors. This one is D2, 5.0 meters at 30 degrees north of east. So now I'm ready to do my resultant. And the resultant is literally a line that is connecting the what? Tail of the first vector to the head of the second. Now, the thicker the marker or pen you're doing this with, the fuzzier your numbers are going to be. But you want to get this as exact as possible. Okay, that's my resultant. Now, I'm going to measure the distance of that resultant line, and that's actually the number of meters of travel. So I have 43.5 centimeters. We're doing 2 centimeters equals a meter, so 21.75. 43 divided by 2, 21.75. Huh?
I got 17.
Okay, so I screwed up again. 43, so the 40 divided by 2 is 20.
Right.
The 3 divided
Your
by
math is
2 is... Oh, you're saying your line is different lengths.
Yeah.
Yes, okay, that's fine. Now, we also have to get the heading, because that distance alone is not sufficient to tell us where we are. So we're going to take our protractor, set the bubble right there, and we're going to mark this. It's really tough with a thick line, so I'm getting at about 12 degrees north of east. That is a complete answer. That is a graphical vector. When you learn how to do these algebraically, you can use this method to check yourself. Okay? In the meantime, it's an approximation. Now, somebody said, well, I got 17 meters. What's the range of answers we have? And I'm going to stop the video now, and we'll go back to Doceri. We'll pick up the recording here. What are the range of values that people are getting for the resultant? I heard a 17 meters. What else do we have? 17? 16.6? Anything else for the resultant? Now, my sig figs are terrible. Yes, is that what you were going to pick on?
I have a different degrees.
Okay, so we've got a range of values so far for the resultant, and it seems like all of you are getting a smaller number than I am. Here are the cautions with graphical vector analysis. A little change in where your pen or your pencil or your marker lands can make a big difference. I'm generally pretty good at making sure these line up because I know how significant a differences that can be. So I'll assume until you prove to me otherwise that I'm closer to the true value. I could be wrong. It's happened before. It happens plenty. But there are typically a range of values for graphical solves. So it's one where on a test, I'm not expecting that you'll get 21 point, what would we be able to sig fig this to? 21.3 or 21.8. You might get, very often what I'll do is say a little bit on either side of my answer because I got a lot of practice doing these. So typically I will say, like here I might say 20 to 23 if you're in that range. Because we don't typically use graphical vector analysis for real precision answers. We use it to check our algebraic answer. We use it for sort of a quick and dirty answer to arrive at a value that we think is reasonable. So this is a little bit like Fermi estimates in that way. Now, the 12 degrees north of east, what other values are people getting? 10? 9? 8? What did you guys get? You have 10? Okay. Now, the other thing is my marker line is so fat that my marker line actually occupied the space from 10 to 13. When you're doing it with pencil, you're getting a much better level of precision. I would totally believe that this could be 10 degrees. Again, like I said, my marker line occupied a big wedge of space. Okay, questions, comments on graphical analysis of vectors? FIP quiz tomorrow on them. Okay. Somebody, let me mention one thing before we leave these. Somebody said, well, the resultant is just the hypotenuse. It often is, and the first kind of resultant that we're going to work with solving algebraically is in fact the resultant for perpendicular vectors. So I'm going to just briefly introduce this. Quickly touch these bases. I'm not sure if I touched them in the video or not, but I want to make sure that they're covered well. So when we're looking at vectors in a diagram, and you probably have figured this out relatively recently in doing your mapping for your lab, you can move a vector parallel to itself. So if you think about, and you can add them in any order, and this is directly related to the lab. If you think about maneuvering in an urban area, and many of us don't have a whole lot of opportunities to do that, but some of you will get them very soon, I'm sure, as some of you go off to college, perhaps in urban areas. Come on. So if I'm drawing a few sort of, I could cut and paste. I could copy, huh? Duh. As we look at, if we think of these as like city blocks, and we want to navigate around them. And if I am trying to get from some point here to here, does it matter, whoops, no, copy, if I go 3 blocks east and then 3 blocks north, or can I go 3 blocks north and then 3 blocks east? Can I go here and then here? Yeah. Can I go here and then here? Yeah. Could I go here and then 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 here? Yeah. Doesn't matter. Doesn't matter in what order you do them. When you're adding them up, it doesn't matter if you move all of these parallel to themselves, because guess what? In the end, lo and behold, same difference. Whoops. You can move them parallel, it doesn't matter. And that's really useful when we start doing forces stuff. So it does not matter if you add them in any order, it doesn't matter if you move them parallel to themselves. Great. So the other important bits to know about vectors, and you kind of already know that you can subtract them by adding their opposite. So which groups here figured out really early, I know one of them did, well, if we just take all the easts and subtract them from all the wests, then we get a total distance we have to move east-west. Yeah, because what is 10 meters north but negative 10 meters south? That's all that is. So 10 meters north plus negative 10 meters south means you're not going anywhere. You're just staying where you are. When we look at vectors and we multiply them by some scalar quantity, we still have a vector when we're done. So if you double your speed and your initial speed was v, you're now going 2v. If you cut your speed in half, you're now going 0.5v. When we get into forces, we do a lot of problems where, the force on the object from this direction is twice the force on the object from that direction. Well, one is F, one is 2F. And you guys pretty much get that. I think most people come in kind of having a grip on that. When we are doing vectors, we stick with that traditional Cartesian coordinate system we've been using. X-axis is parallel to the ground, y-axis is perpendicular to the ground, just like we did in one-dimensional motion. When we get into forces, we'll start to do things where we do what's called tilting the x-axis, but we don't have to do that yet. So, oops. Jeez Louise, Moser. Okay, so when we are doing perpendicular vectors, so this is that city block problem. You know, if you're going directly along the cardinal points of the axis, it's really easy to use the Pythagorean Theorem. It is your friend. So we'll do one with that because Pythagoras is useful for getting the magnitude of the resultant. So we'll do that first, and then we'll talk about how to get angles. Okay, so if we go, and now we don't have to worry so much about scale. If I go 15 meters east, and I turn, and I go directly 5 meters north, what is my resultant? How do I find it? Well, first I'm going to draw it. Whoops, I didn't mean to keep that same color. I'm going to draw it. So I'm going to make sure I've got these labeled. So I have displacement 1 is 15 meters east. Displacement 2 is 5 meters north. My resultant is this red line. How do I find it? Pythagoras. Perpendicular vectors are easy, easy, easy to solve. So we know d1 squared plus d2 squared equals r squared, the resultant squared. So the resultant is going to be equal to the square root of d1 squared plus the square root of d2 squared. So let's plug in our numbers. Resultant is equal to the square root of 15 meters squared plus 5 meters squared. Yep. 15.8113883 meters. Our resultant, we want to take our sig figs. Oh, shoot. You know what? Let's pretend that I wrote that better, and that's 5.0. Shall we? Let's get 2 sig figs out of this, please. So our resultant would be 16 meters. But that doesn't tell us where we are. So what other thing do we need? What we're looking for is this angle here. So to start with, because this is the part of the whole heading thing that confuses people the most, so do it first. And that is, this is going to be what of what? North of east. Here's how to not screw that up. If you struggle with this, you put your writing utensil on the line you're starting on. That's your east. You're heading north from the east. And I literally draw myself a little arrow for that angle because I screw it up less that way. So how do we get that angle? Trig! So when we want to find the angle of a resultant, the thing that we most commonly use, especially with the perpendicular vectors, is tangent function, because tangent is what? Opposite over adjacent. I will put up my SOHCAHTOA posters. I don't know where they are. I'll have to make new ones, but I've always had SOHCAHTOA in my room because it helps. You know SOHCAHTOA? Okay, good. And it's just fun to sort of mutter under your breath and people think you're crazy, and I like that. So if we want to use tangent to find the resultant here, okay, so we want that angle. Here's the other thing I do to prevent myself from screwing up. Have you noticed that I do a lot of things to prevent myself from screwing up because I screw up a lot? So when I am figuring out what are my opposites and adjacents, I literally draw myself a little line. That's my opposite, and a little line with a kink in it. That's my adjacent. So the way this is expressed, we call this angle theta. And what we say is that theta is equal to the inverse tangent function, tan minus 1, of, and this would be of d2 over d1. Because d2 is our opposite, d1 is our adjacent. So theta equals inverse tangent of 5.0 meters over 15 meters. So you do second function tangent, 5 divided by 15, and close your parentheses. Who's got a raw number for me? Answer of 18.43, and I'm sure you have the same trailing digits as I do, 94882, and on and on and on. What's our final sig fig answer? 18 degrees. And so our full answer, when I ask you for a resultant in a problem like this, your full answer should be 16 meters at 18 degrees north of east. Okay? A quick word about compass. Well, we'll do that tomorrow. I'll assign the section review problems. You can get started on those. We're going to have a FIP quiz tomorrow on graphical vector construction. Okay, so assigned is page 91, the 3A problems, numbers 1 through 4.